Okay, linear vector spaces, or LVS. I will be going over the basic properties, subspaces, intersections, direct sum, nullity and rank properties. Okay, so first, the basic properties. So there's three properties that linear vector spaces must have. The first is closed under addition and scalar multiplication. Second, all vector spaces must contain the zero vector. And lastly, every vector in a space has an additive inverse. So what this looks like, say for closed under addition and scalar multiplication, in the example we have here with A and B being having two vectors multiplied by these constants, we could just substitute in some numbers, say like 1 and 3, and it would be the same thing as having L and LV and LU multiplied by these numbers. Having a zero vector is pretty self-explanatory, and having an additive inverse is might need an example. So if you have a set of odd integers and you add 3 and 5, the result is an even integer. This is not contained in the set of odd integers, so this would not be an odd vector space. So that would be an example of some vector having space having an additive inverse. So subspaces, intersections, and unions. A subset W of a vector space V is called a subspace of V if W itself is a vector space that is closed under addition and scalar multiplication defined on V. A theorem. If V and W are subspaces of U, then their intersection is also a subspace of U. So the intersection between the two subspaces V and W is not empty because it contains the zero vector of V. Since V and W are subspaces of U, they contain vectors v1 and v2 that are not closed under addition and scalar and multiplication. Hence, their intersection must also contain vectors v1 and v2 and are closed under addition and scalar multiplication. Therefore, we can go on to the theorem that V and W does not require for the union of V and W to be in U. LVS direct sum. The direct sum is vector spaces can be expressed as the partition of subspaces where the intersection between the subspaces only contains the zero vector. For example, the space of polynomials can be divided into two subspaces, one that contains polynomials of odd power and the other of polynomials that contain polynomials of even power. We have a proof here as well. If we have V inside of W, then the orthonormal basis of W is part of the orthonormal basis of V. So let's say that the orthonormal basis for V is some S basis, and the orthonormal basis for W is some S1 basis. Then since the W perpendicular vectors are orthogonal to W vectors, and the bases of V are orthonormal, we have a subspace 2. Basis for W perpendicular, and any vector in V can be written as the linear combinations of basis and W orthogonal, or perpendicular. Therefore, V plus V perpendicular, V is equal to W plus W perpendicular, and W and union W perpendicular only have a intersection of the zero vector. These two conditions give the result. V is equal to W and W perpendicular, or direct sum of W perpendicular. Okay, nullity and rank. There are four fundamental subspaces of linear vector spaces with the matrix elements: the null space of A, the null space of A transform, and the column space of A, and the column space of A transform. The rank of a matrix corresponds to the number of linearly independent rows or columns. The basis for column space can be found by getting the matrix in RREF, row reduced echelon form, and reading off the columns of A with leading ones. The basis for null space can be found by getting the matrix in row reduced echelon form and solving for the homogeneous system AX is equal to 0. Here we have an image of what the visual image of what the null spaces and call spaces kind of look like related to each other. Next, the inner product.